All right. Hi, my name is Benjamin Berczi. I am from the University of Nottingham, and I will be talking about gravitational collapse of quantum fields. This is based on work in collaboration with Paul Suffin and Zhu Su. All right, just a little bit of introduction and motivation. So the two main avenues of motivation is the critical collapse, first discovered by Choptwick, and Hawking radiation. In Choptwick critical collapse, it was discovered that on the onset of a critical black hole formation, there's a university and scaling invariance that was not anticipated. And an obvious question is would be asking if this survives quantum matter as well, and not just classical matter. So we need a way to simulate quantum fields collapsing. And in terms of Hawking radiation, to see it from physical black holes is there's no chance for it because it's so weak. And in numerical simulations, it has been only seen in 2D or analog models and not in 4D yet. So again, we need to simulate quantum fields collapsing, but in 4D now. So just a little bit of background of classical collapse. In classical collapse, we have a specific space-time geometry and some matter, and we can derive the evolution equations and simulate the dynamics. In our case, we just have a generic spherical metric and a massless scalar field, just because it's the simplest thing we can think of. And we can just derive the evolution equations easily and simulate what happens. Qualitatively, two things can happen. Either a black hole forms or it doesn't. And we can look at the actual evolution. So in most of these simulations, the initial scalar field is just a Gaussian that is put at some spatial value. So here it's at r equals 5. And when we start evolving it, it splits into two, one traveling outwards and the other part traveling inwards, reflecting and also starting to travel outwards. Here we can see that there is no black hole formed at t equals 20. So we can't see anything at r equals 0, but we can look at what happens to the lapse function, which is just a function here, which is chosen to be singularity avoiding in these simulations, so that when the lapse approaches 0, we know that there's a significant curvature there. So here we can see that it doesn't form a black hole, it just returns to its asymptotic value, which is just 1. In the black hole formation, however, we have the same evolution, but at the very end, there's some part of this scalar field staying at the middle. And we can see this at the lapse functions evolution as well, since it collapses on itself as well. That's a sort of the collapse of the lapse phenomenon. When Choptwick studied the critical amplitude, so the amplitude that just about forms a black hole, he found this sort of scaling, which is not dependent on the initial data whatsoever. And it has a sort of this universal proportionality constant between the difference between the amplitude and the mass of the black hole, which is very interesting. All right, let's turn to quantum collapse. So in our formalism, all we do is to promote the classical scalar field to be a quantum operator and expand it in terms of its spherical modes. And here you can see that we have the spherical harmonics and the mode functions separated. Right. So now our system is the same. We have we have the metric, which is classical, and we have the stress tensor, but now it's an operator. So in our evolution equations as well, we have to put it in sort of these expectation values and along with the quantum scalar operator as well. So question is, what sort of quantum state do we choose? Well, in our formalism, we choose a coherent state, which is just a special minimally uncertain state. And this ensures that the expectation value of the scalar is interchangeable with the classical field. So they obey the same equations of motion. So our field equations using the coherent state become these. And so this looks very similar to the classical case, but we just have some extra mode function equations of motion. So why is this useful? In more detail, the stress tensor needs objects like this one, And we can see that it separates into sort of two parts, one containing an H-bar and the other one doesn't. And so we can sort of say that the full quantum simulation is built up by this classical part plus some extra fluctuations due to the quantum modes. The question is, how many modes do we have to use? Of course. And in practice, we see that 5 to 10,000 modes produce realistic results. So we do need a lot. Let me show you some results. So in the quantum simulation, we have the same initial conditions. So just a Gaussian somewhere at a spatial location. Here, the only difference is that I put it more closely to the center, because the quantum modes, when one simulates them, they are quite, it's quite difficult to maintain their stability. So we want the simulation to be as quick as possible. So here, in this case, there is a black hole formed, and because of the singularity avoidance again, the time freezes at the center. So we see this, that the scalar froze here, and a horizon forms. And here we use 5,000 modes. So this looks exactly the same as in the classical case. It's very hard to see by eye to see what would be the difference. But what does show some difference is the stress energy tensor components. So here is just the full expectation value. So this is classical plus fluctuations, but we can in fact look at just the difference. But let's look at this for now. So we can see that it bunches up. So the biggest values are around r equals 0, which is what we expect, since that's where the black hole's location is. And if we look at the difference, on the other hand, we can see that's not bunched up at r equals 0, which is very interesting, but it's more bunched up around the horizon. So again, here I'm showing just the quantum effects, sort of. So the contribution solely from the quantum modes. And again, we can see that they bunch up around the horizon, but of course, they are quite sort of arbitrary shapes. So what we wanted to make sure that we're not seeing anything, just a numerical artifact. So we sort of did this convergence plot where we did the simulation, but with increasing number of quantum modes to see if they converge onto some real quantum effect values. And we can see that it does. So around 5 to 10,000, it sort of doesn't change anymore. So that's a really good sort of indication for us that we see something that's actually physical. And adding, hundreds of thousands of new quantum modes hopefully shouldn't change the evolution too much anymore. So we see new quantum effects, we can say that. And we also looked at Choptic scaling, and we found that it does still obey. So even in semi-classical simulations, we see this sort of scaling behavior, which is very interesting. And it fits just the same scaling law with the same exact scaling constant, which is the 0.37. All right, let me just summarize very quickly. So by the virtue of these coherent states, we can build up a semi-classical simulation on top of the classical one. However, we do need to use a large amount of mode functions, which creates a lot of computational power that is needed. And also, we see that Choptic scaling survives semi-classical collapse. So we expect that even quantum matter shows this sort of scaling and universality at the critical sort of point of black hole formation. And we see that there are new quantum effects. But what they are, we don't exactly know. We can't really say that they are Hawking radiation, even though they're just around the horizon. We have to look at sort of correlation functions and things like that to make sure that it actually is. So yeah, there's a lot to do. Thank you for listening.
Thank you very much. There's a couple of questions coming in, so I'll go directly over to them. So the first question is from Julianne. It says, can you elaborate on your choice of coherent states? What do they fulfill?
Yeah, sure. So, I mean, these are just some specific states that one can derive, and all they do is they minimize the sort of the Heisenberg uncertainty on the state itself. I mean, yeah, they just have to be sort of derived and chosen, and then that's all I can, I think, really say about them. And I think I can see the other question as well. Is that from Marion?
Yep, go ahead.
Okay, so when you say 5 to 10 modes gives realistic results, what do you mean by realistic? So yeah, what I mean by realistic, I couldn't show you here because I didn't have time, but if I go through, so when I mean realistic, I mean when we build up the quantum vacuum, so there the stress energy tensors would have to vanish, and when we keep adding modes, it vanishes better and better. So you can see that it diverges, but at this end central spatial value, it's flat and it's approximately 0. So that's what I mean by realistic, that in the vacuum, the stress energy tensors vanish at a sufficient spatial location, at a sufficient with a sufficient small error in them. So here it's 10 to the minus 6, but we can see when we look at the stress energy tensor expectation values, it's 80. So there's a 8 orders of magnitude difference. So we can say that then it doesn't matter that we have these sort of differences here. So our systematic error is sort of overpowered. That's what I mean by realistic. Okay,
there's another question coming from Martin Rogers.
Any speculation about what the new quantum effects near the horizon give rise to observationally? Well, I really want them to be Hawking radiation, because that would be amazing if we could just see it. But I did look at these correlation functions that I mentioned, and they don't have the same sort of signatures as Hawking radiation should have, because that would be a sort of a very unique signature that we don't see at this point. But that could be just because of the fact that our black holes are not producing strong enough Hawking radiation, so they're too big. So what I'm trying to work on now is to make smaller black holes, because that should have a larger flux of Hawking radiation, which hopefully shows up in correlation function signatures, if that makes sense.
I think so. Can I ask a question before we wrap up for the session?
Yes.
When you show your plots of the expectation values of the stress energy tensor, is there actually angular momentum there? Or there's a radial profile for angular momentum?
Well, so that would be the TTR.
Not the T theta theta? Am I reading the wrong thing?
Oh, so sorry. So that would be the, which one?
T theta theta. I'm assuming that theta was an angle.
Yes, yes, you're completely right. So in the classical case, that component is completely 0. But of course, because we allow quantum fluctuations, they can sort of leak in. So yeah, we do have some sort of fluctuations in that direction as well.
Is the net angular momentum still 0?
Yeah, classically, so in the expectation value, it is still 0. It's just these fluctuations that can be sort of non-zero.
But if you were to integrate this curve over R, would the result be 0? Is angular momentum conserved, is what I'm asking.
I think yes, it should be. It very, very well should be conserved. Yes.
Okay.
But yeah, that's an interesting question. I haven't thought about that too much. Thank you.
Right. Well,